Okay, so testing. Good. This works well. Yeah, thank you very much for the invitation. I'm very glad to be here in person again. Okay, so today I'll compare what we know about sum of squares lower bound to what we know about low degree polynomial lower bounds. So in this talk, I'll first give some introduction. I'll then describe how low degree polynomial lower bounds are related to sum of squares lower bounds. I'll then describe our current knowledge about sum of squares lower bounds. And if there's time left, I'll try and give some intuition for the low degree conjecture. As a note, this talk is closely connected to Prasad's fourth bootcamp talk, but it's from a different perspective. Okay, so I'll be moving at a brisk pace, but please feel free to stop me if you have any questions. Okay, so first an introduction. So today we'll be considering distinguishing problems, where we're trying to distinguish between a random and a planet distribution. For example, in the planet Clique problem, the random distribution is just a random graph where each edge is there or not there with probability 1/2. In the planet distribution, we take a random graph and we plant a clique of size k in it. Another example is tensor PCA, where in the random distribution, the entries of the tensor are just random noise. And in the planet distribution, we have the random noise plus rank 1 component. So here's an example for planet Clique. So here one graph from the random distribution, one graph from the planet distribution. Can you tell which graph has a 5 clique? Just call it out if you see it or take a guess. It's actually the one on the left happens to have more edges, but it's actually the one on the right.
More edges?
Yeah, it's an optical illusion because the one on the left has its edges are hidden on the outside.
You re-randomize the slide between talks?
I did previously, but this is actually the same from my last iteration of the sum of squares course a few years ago. Okay. Okay. So anyways, in the low degree polynomial framework, we ask: is there a low degree polynomial which distinguishes between the two distributions? More precisely, is there a low degree polynomial f such that the expected value over the planet distribution is large, but the expected value over the random distribution is 0, and the variance is at most 1? And if so, then we have a low degree polynomial lower bound. So in the sum of squares framework, so sum of squares is a proof system, so it's most naturally applied to certification problems, where we try and certify that a random input does not have some hidden structure. That said, we can apply it to distinguishing problems with the pseudo-calibration framework, where I won't go into this too much, but we first use pseudo-calibration to obtain pseudo-expectation values for the random inputs. And then we construct the corresponding moment matrix, and then we analyze whether this moment matrix is PSD. And if it's PSD with high probability, then we have a sum of squares lower bound. Actually, more precisely, the pseudo-expectation values will satisfy all low degree constraints satisfied by the planet distribution. So here's a summary. Actually, okay, so the low degree conjecture says that if we have a sum of squares lower bound where the pseudo expectation value of 1 is well behaved, and yeah, I'd say for sum of squares lower bounds, the pseudo expectation value of 1 is pretty much always well behaved, then this implies a low degree polynomial lower bound, as I'll discuss next. So the low degree conjecture is for the other direction. It says that it conjectures that for symmetric distinguishing problems, if we have a low degree polynomial lower bound, then we'll have a sum of squares lower bound for a noisy version of the problem where we add some additional noise to the planet distribution. Okay, so but before I move on to the next part, are there any questions you'd like to ask now?
Could you review briefly for folks what it means for pseudo expectation of one to be well behaved?
So I'm gonna talk about that in the next part. Okay, so I'll now just describe the relationship between low degree polynomial lower bounds and sum of squares lower bounds proved using pseudo-calibration. In particular, low degree polynomial lower bounds correspond to the pseudo expectation value of one being well behaved. Okay, so in Sam's thesis, he observed that the pseudo expectation value of one is the low degree likelihood ratio for the input being from the Planet distribution. So what I'll show in this part is that if there's a low degree polynomial whose expected value is large on the Planet distribution, and whose variance is most one on the random distribution, then the variance of the pseudo expectation value of one will be at least c squared. Okay, so but before I do this, I have to give some background. So here we'll have a vector space of polynomials. We'll have an inner product on these polynomials, which is the expected value of their product on the random distribution. And then we'll have an orthonormal basis of Fourier characters for this inner product. So now Fourier decomposition is just that for any polynomial f, we can decompose it as the sum of its Fourier coefficients times the Fourier characters. And then the low degree projection. For the low degree projection of f, we just take the low degree Fourier characters. Okay, so I'm going to be a bit hand wavy for this part. I should try to give a little bit of intuition for what we want to do with the pseudo expectation values. So our general setup is that we'll have for these problems we'll have solution variables corresponding to the Planet structure that we want to try and find. We'll have our Fourier characters on the random input. So for example, in the Clique problem, we can set it up so that we have solution variables xi, where we want that xi is 1 if the vertex I is in the Planet Clique and 0 otherwise. And then our Fourier characters correspond to sets of edges, so they're the product of the individual Fourier character for each edge, which is 1 if the edge is in the graph and -1 otherwise. And these form an orthonormal basis if you look at the expectation over a random graph. Okay, so now for the Planet distribution, each Planet instance will assign values to the solution variables, and thus assigns a value to any polynomial in the solution variables. So now, unfortunately, I can't go into this too much, but what we need to do to construct pseudo expectation values is for a random instance I, we have to assign a pseudo expectation value, the pseudo expectation value of p, to each low degree polynomial p in the solution variables. Okay, so the pseudo-calibration technique for doing this is as follows. Given the random input I, we'll take the pseudo expectation value of p to be the low degree projection of the probability of the planned distribution of having the instance I divided by the probability in the random distribution of the instance I times P of I. So the reason that the reason that this works well is as follows. So if we look at the expected value over the random distribution of the pseudo expectation value of P times chi I. So here we just plug in this expression here, and then observe that this is just equal to the expected value over the planar distribution of P times chi I. So what this is saying is that as far as low degree tests are concerned, the pseudo expectation values over the random input behave like the actual solutions over the planar distribution. And this gives us the following equation. The pseudo expectation value of P is the sum over low degree chi I of the expected value over the planned distribution of P times chi I times chi I. So once we have the random and planned distributions, it's a mechanical process. Okay. Anything that you'd like to ask so far?
What is the P was P is a polynomial in solution variables, right? So P of I means that there's some solution associated with instance I.
Yes. So here for instances from the planned distribution, they'll also assign values to the solution variables.
Okay.
So right, either the probability over the planned distribution of having I will be 0, or like P of I will be well defined. I should also note, as in your thesis, if we didn't take a low degree truncation of this, then this would be well defined. But however, it would be 0 on almost all instances. In particular, it would be 0 on any instances which are not in the planned distribution. Yes.
Is it easy to verify this is an actual pseudo expectation, like the P of P squared positive? That's what I'm referring.
Not at all. That's where all the technical challenge. All the technical challenge is. So yeah, there's no guarantee that this will give a valid pseudo expectation value, but it does work well in many cases. Okay, so a canonical example is playing a clique, where like if we take the again random distribution where we have a random graph, and now we'll look at a slightly different planned distribution for simplicity, where we start with a random graph and put each vertex in the planned clique with probability k over n. Now, if we define x of v to be the product over I and v of xi, so it's an indicator of whether all the vertices of v are in the planned clique. So I claim that the expected value over the planned distribution of xv times chi e is k over n to the number of vertices which are either in v or are an endpoint of some edge in E. So the reason is that if all these vertices are in the planned clique, then xv is 1, and all the edges are present, so chi e is also 1. if some vertex v is not, if some vertex here is not in the plane of Clique, then xv will be 0. And if some vertex, if some endpoint of an edge in E is not in the plane of Clique, then one of these edges will be outside the plane of Clique. So it'll have expected value 0 over the randomness of the rest of the graph outside of the plane of Clique. So these give the following pseudo expectation values. Okay, so now let's analyze the pseudo expectation value of 1. So here's the pseudo calibration equation. So as a special case, the pseudo expectation value of 1 will be 1 plus the sum over non-empty low degree chi I of the expected value over the Planar distribution of chi I times chi I. And now let's assume that we have a low degree polynomial f such that the expected value over the Planar distribution of f is c. The expected value over the random distribution of f is 0, and the variance of f is at most 1. So now here's the proof. And the note, all sums below will be over low degree non-empty chi I. So let's write f as the sum over I of ai times chi I, and let bi be the expected value over the Planar distribution of chi I. So now the pseudo expectation value of 1 minus 1 will be by this formula, it'll be the sum over chi I of bi times chi I. So now the variance of f will be the sum over I of ai squared. And the variance of the pseudo expectation value of 1 will be the sum over I of bi squared. And now using Cauchy-Schwarz, C is the expected value over the Planar distribution of f. Since f is the sum over I of ai times chi I, this will be the sum over I of ai times bi. Using Cauchy-Schwarz, this is at most the square root of the sum over I of ai squared times the square root of the sum over I of bi squared, which is the variance of f times the variance of the pseudo expectation value of 1. Now, since the variance of f is at most 1, rearranging this, this gives us that the variance of the pseudo expectation value of 1 is at least c squared. Okay, so here's a picture for how low degree polynomial lower bounds are related to sum of squares lower bounds proved using pseudo calibration. Right, so the low degree polynomial lower bounds correspond to checking that the particular entry, the pseudo expectation value of 1, is well behaved, whereas for sum of squares lower bound, we have to show that the entire matrix is PSD with high probability. Okay, so this means so sum of squares lower bounds using pseudo calibration are strictly stronger than low degree polynomial lower bounds as they involve analyzing the entire Moore matrix. And there are many interesting techniques involved in proving sum of squares lower bounds, which I can talk about for a long time, but now is not that time. That said, low degree polynomials are an excellent heuristic for determining the computational threshold where a problem is hard, and they're much easier to prove than low degree that should be sum of squares lower bounds. Okay, so any questions before I move on to the next part where I'll describe what we currently know about describe current gaps between sum of squares and lower bounds and low degree polynomial lower bounds. So there we are.
It's like, sorry, yes, yeah. Is it easy to see that there's special case, the pseudo expectation of one? Oh, previous slide, sorry. Yeah, is it easy to see the second line? Yes, that is the pseudo expectation.
Oh, yeah. So here, P is just one. So that's why this vanishes. And then when chi is the empty set, then chi itself is also just one. So that's why we just have the one term there.
Okay, yeah, cool. Yes, thanks.
No problem.
Sort of breaking maybe 5 minutes, so I'm gonna take a.
Okay, so yeah, that should be sufficient for the third part. Probably won't have time for the fourth part. Okay, so yeah, so far there's a lot of evidence for the low degree conjecture. The thresholds for SOS lower bounds and low degree polynomial lower bounds match for planet clique, tensor PCA, sparse PCA, and random CSVs. That said, there are still significant gaps between known SOS lower bounds and known low degree polynomial lower bounds. Okay, so here's one subtle issue, which is that current SOS lower bounds are delicate, as they're sensitive to the choice of plan distribution. So for example, for planet clique, a random distribution is GN1/2. The plan distribution we used for in DHK plus to the almost sum squared lower bounds for planet clique is to put each vertex in the planet clique independently with probability k/n. This makes the pseudo-calibration calculation simpler, but the problem is that we really want to satisfy the constraint that the clique has size exactly k, and this only makes the planet clique have size approximately k. So our desired planet distribution would be the planet clique of size exactly k. So here, Schwarz-Pong recently fixed this issue by proving a sum of squares lower bound for the desired planet distribution. So another example is tensor PCA. Right? So in the random distribution, we have a tensor T with Gaussian entries. So the plan distribution using the current lower bounds, we take a vector v where most of the coordinates are actually 0. There's actually a somewhat sparse vector. If we instead took v to be a vector with coordinates plus or minus 1 over square root of n, then for an annoying technical reason, which I won't get into, the current techniques from analyzing the moment matrix don't quite work. Okay, so I'll now describe two interesting examples. So one is something which I've heard called parallel pancakes. Another is independent set on sparse graphs. So consider the following random and planned distributions. So in the random distribution, we have m random vectors in Rn with Gaussian entries. In the planned distribution, so we'll first choose a hidden direction v, and then we'll choose and that there'll also be some distribution A. And then we'll choose our m vectors so that orthogonal to v, they're nice and Gaussian. And in the direction v, they're distributed according to A. Okay, so there's this is a basis for the statistical query lower bound on this problem, where if A matches the first k moments of a Gaussian and the total variation distance between a Gaussian and it is finite, then the lower bound when m is much less than n to the k plus 1/2. And as recently shown by Sam Salil and others, yeah, I apologize for not having the names off the top of my head. Statistical query lower bounds are very closely connected to low degree polynomial lower bounds. Now for sum of squares, so for the special case when A is just -1 and +1, we have an SOS lower bound when m is at most n to the 3/2, which was used to prove an SOS lower bound for the Sherrington-Kirkpatrick problem. As a note, here we have a low degree polynomial lower bound when m is at most n squared. One interesting question is to try and strengthen the SOS lower bound from n to the 3/2 to n squared, and another open problem is to prove SOS lower bounds for more general distributions A.
Take about 1 minute to wrap up, just so we don't lose too much of the slip in the schedule.
So I only have a few more slides. Okay, so the last example I'll give is independent set on sparse graphs. So given a sparse graph G with average degree average degree D, does it have an independent set of size k, roughly n to n over this d to the 1/2 plus epsilon? So here we can have the random distribution be a G and D over n graph. So a naive plan distribution is to start with this graph and then put each vertex in the independent set with probability k over n. The problem is that it's easy to distinguish these distributions. In fact, counting the number of triangles is efficient. So what can we do? So for low degree polynomials, Salil and Alex recently got around this by showing a lower bound for the recovery problem. They showed that if you even though there are these global distinguishers, if you look at a given vertex I, there's no low degree polynomial which distinguishes whether I is in the independent set or not. And for sum of squares, we recently showed that, so this paper will be posted in a few weeks, that even though pseudo-calibration fails, we can tweak the pseudo-expectation values to prove a sum of squares lower bound on the certification problem, proving that this random graph does not have this large independent set. So the open problem here is, can we find a planned distribution for independent set on sparse graphs, which is hard to distinguish from G and D over n? Okay, and I'll end here.
Thank you, Aaron. Thanks, Aaron Pradesh, for tackling some hardcore technical material in our first 90 minutes. We will see you all back here at 11:10.
Yeah.